Hello. Just for fun, I thought I'd do some level 3 frequency response questions as well. Let's have a look. At low frequencies, you would expect the inductor here to be effectively a short circuit. So at low frequencies, we would expect the circuit to look just like this. This type of problem, it's often helpful to consider what they look like at low frequencies and high frequencies. And at very low frequency approximation, we would have that. The inductor is effectively a short circuit, the capacitor is effectively an open circuit. So we would expect at low frequencies X to be smaller than I by a factor of, let's see, that would be 20 times log 10 of 4K7 divided by 15K plus 4K7 minus 12 dB. So, and that is indeed where B and D start off. So immediately we can eliminate A and we can eliminate C. Next. Right, let's have a look at what B and D do. Well, at very high frequencies, they're both going down with the same 40 dB per decade gradient, so we cannot quickly tell the difference between them on that respect, but they have very different 3 dB points. Now, where on this circuit would the poles lie? And you can sort of try and use some engineering approximations to work these things out faster. Here we have a Z1, if you like, the top term of our potential divider equation, which is going to start off at 15K, and as the frequency increases, it's going to get bigger. And the point where that doubles would be the point where the impedance of the resistor and the magnitude of the impedance of the inductor are approximately the same. In other words, that would be the point where the 15K was equal to the magnitude of j omega L, and the L is 470 milli. Right, at what frequency does that occur? Well, that would just be omega equals 15K divided by 470 milli, which is, quick bit of calculation, 15K divided by 470 milli is that divided by 2 divided by pi. To get it into hertz, that would be about 5 kilohertz. So I'd expect there to be a pole caused by the increase in impedance of that inductor somewhere around about 5 kilohertz. B seems to have a pole around about 600 hertz. That's way too low. And the other pole, you can see that B heads down at a gradient of 20 dBs per decade for this region, and then it tilts again at around about here, and that is about 275 kilohertz, the point where it changes gradient again. That's much too high. However, D does go down from about minus 12 dB to about minus 15 dB at around 5.75 kilohertz, which is pretty close to where I would expect the effect of that inductor to start kicking in. The other pole here will be due to the fact that that capacitor is beginning to have a impedance similar to this resistor. But if we've eliminated B because the poles are at the wrong frequencies for this LR at the top, the answer must be D. Great. No need to do any terribly difficult calculations looking at the poles and zeros in the whole circuit. Let's try another one. Resonant frequency. Right, what is the resonant frequency of the poles? Well, this is quite straightforward if you know the trick. And the trick is that the resonant frequency of a circuit in which there's a capacitor and an inductor is always given by the frequency at which the impedance of the capacitor is equal and opposite to the impedance of the inductor. In other words, we need that j omega L is equal to minus 1 over j omega c. If we multiply through by j, that just gives us that omega L equals 1 over omega c. In other words, omega is the square root of 1 over LC. And that is the resonant frequency. So, we just need to take the square root of the inductor, 4 millisieven, multiply it by the capacitor, 33p, take 1 over that, and remember that that is in radians per second, so we need to divide by 2 and divide by pi, and we're there. Those ones you can do quite quick. It's working out the Q factor that takes a bit longer. Right, 1, 0 at 0 Hertz, 2 poles with a resonant frequency of 1.59 kilohertz and a Q factor of 6.8. What is the value of the inductor? Well, if you've worked through all of these circuit configurations, you may already know what the formula for the gain of this circuit is. If not, you can readily work it out. We've got an input here going through a resistor, then there's a capacitor down there, and an inductor down there. And that's the output. Right. So, again, standard potential divider equation. It's the impedance of this network divided by the impedance of this network plus the impedance of that network. So, H of j omega would be equal to j omega L divided by j omega c over j omega L plus 1 over j omega c all over that lot again plus r. First thing to do, multiply through by this term. That would give me h of j omega being equal to j omega L over j omega c divided by j omega L over j omega c plus r times j omega L plus r over j omega c. Multiply through by j omega c, and we're left with j omega L over j omega L minus omega squared LRC plus r. And if I divide everything through by r, we end up with j omega L over r over 1 plus j omega L minus omega squared, so L over r rather, plus omega squared times LC. And compare that to the standard form of the second order response, which is that the denominator is given by 1 plus j omega over q omega naught minus omega squared over omega naught squared, where omega naught is the resonant frequency and q is the Q factor. We can see in this case that omega naught must be the square root of 1 over LC, and q is once again r over L divided by omega naught, which would be multiplied by the square root of L over C, which is r times the square root of C over L. Same formula that we've seen before. Right, here we're just asked what value the inductor must have. And rather than doing all of that stuff, the trick here is to find the fastest way to do it. And the fastest way to do it is to ignore the Q factor value. You don't need to know. You know that the resonant frequency is 1 over the square root of C times L. So, if I take the resonant frequency here, which is 1.59 kilohertz, multiply it by 2 and pi to turn it into a frequency in radians per second, if I square that, then what I will end up with is 1 over LC. If I do 1 over that, then what I've got there is L times C. So if I divide that by C, I must have L. Great. Not that hard, actually. The important formulas to know are this one and this one for the resonant frequency and the Q factor of a circuit which has a resistor, a capacitor and an inductor in it. Okay. Good luck.